This is X4 questions 6 and 7, which are related to local search. So first, this is a local search problem in 3D, so you have the same question in 2D, so the way to solve it is actually exactly the same, except for you need to visualize things in 3D. Starting from a point, you can move up, down, left, right, and front and back, also. So there are 6 successors in total, and we are on some kind of 3D space that are bounded by, that are kind of measured. The score is measured by this, and they're bounded by -6 plus 6 and -7 plus 7, and so on. So we're in a box, and we just move around the box, and hopefully we hit one of the corners, and that would be the local minimum. So the way to solve this is, first, you are just freely moving around in a box or on a plane, and it's kind of linear, so there's only one global minimum, and so the only local minimum is the global minimum. So we just compute the global minimum, and the next thing is we figure out where among the corners where it is. So let's look at the formula I, j, and k. So the larger the I, the larger the value. So we want the local minimum, so we want I to be as small as possible. For j, the larger the j, the smaller the total value, or I think it's called the score here, but it's just the value function. And in any case, k, the same thing. The smaller the k, the smaller the score. So knowing these, we have the upper bound and lower bound, and there's only one global minimum, so we are basically done. So it means I is as small as possible, and j is as large as possible, which is 7, and k is as small as possible as well. And the question is asking for not the score, so we don't actually need to compute stuff, so that's great. So just enter the vector. And as I mentioned, it doesn't really matter where we start, so the starting point is irrelevant. We just go through, like, move in the correct direction. It's harder to view this in 3 dimension. So in two dimension, if you visualize the score as the, say, the on the z-axis, and then we have I and j, then no matter where we start, we just go like this, and then we hit one of the 4 corners, so we only care about which one is the best one. And again, it doesn't matter where we start. So that's this local search problem. And actually, it doesn't matter what algorithm we use. So here we're doing hill climbing. If you use the other two, again, there's only one global minimum. You always reach there. And the next question is about simulated annealing, and you just need to remember the formula, which unfortunately I don't remember. So let's let me find it maybe. The formula of the probability of moving to a worse state is the exponential of minus f the new state minus f the old state absolute value divided by t. So T is the temperature and T is at time T. But we have a constant, so it doesn't matter. So that's the formula for the probability of moving to a state that's worse, so inferior state. So we want to minimize this probability, so we want this whole thing to be as small as possible. So let's try, if we increase T, what will happen? If we have T as large as possible, so if we increase T, then this whole thing will decrease, and with the minus sign, we use a different color. With the minus sign, the whole thing will increase. And with the exponential, the whole thing will increase, because exponential is an increasing function. So basically, if we increase t, we will increase the probability of moving to a bad state. So here we want to minimize the probability. So we want to have a t that's as small as possible, because if we decrease t, the thing circled in red will increase, and add a minus sign, the whole thing will decrease, and when we exponentiate this, the whole thing will decrease as well. So assuming the formula here is correct, then we should choose a t that's as small as possible, which here would be 6.